me prove what we were supposed to prove last time. So here, let me write the lemma. So we consider a simply connected domain. And we consider a function as a solution to a certain elliptic equation, and denoted by P. The following equation: Laplacian is equal to -2 indeed, and P has just trivial values on the boundary. Then we have to prove the integral of P is always less than or equal to the square root of 4 pi. And the equality is achieved with V is the case. So this is what we are supposed to prove, but I'm going to make a little bit more general statements. Because we want to go from the simply connected patch to multiply connected patch. So now we consider a connective set. So you can allow the patch has a hole. So this region is going to be C. So I'm going to use the notation H1 and H2, HI to denote each hole. And then first statement is going to be there exists I. Here, let's suppose we have the n number of rules. So I runs from 1 to. Then there's going to be a constant I. Such that a unique solution to the following: Laplacian of P is still -2 on the IND in the domain, and P attains these constant values Ci on each boundary of the hole, and P equals to 0 on the outmost boundary. So let me call this outmost boundary D naught. The unique solution to this equation satisfies integral that P and the sigma is equal to -2 times the area of the hole. Here, the n, it denotes the outer normal vector, so it's pointing inward to the domain. So it's outer normal vector with respect to the hole. So this is the first statement. We can choose certain constants so that a unique solution to this equation satisfies this relation. And the second statement is that if P is a solution to this equation, then integral P is always less than or equal to 4 pi, and the equality is obtained only if P is a disk or an annulus. So we are going to prove these two statements. So obviously, the second statement implies this one, because in this case, we don't have any holes, so P simply solves the same equation as this. And in this case, we have the same bound for the integral of P, and the equality achieved when the statistics. Any questions so far? So let's prove the first one. So I'm going to define two functions as solutions to the following. So U is superharmonic function, and U obtains just trivial boundary value. So U is just 0 on the boundary, like on the outer boundary or on the inner boundary. And we so VI goes to the following. VI is harmonic function V, and the VI goes to some constant CI, 1 on the boundary of the ith hole, and 0 on the boundary subtracted H. So VI is just harmonic in the domain, but it obtains the constant value 1 on the boundary. If we choose V1, then that is going to be 1 on the first boundary, but the value of V1 is going to be 0 on the outer boundary and the other boundaries. In this case, we need to constant CI so that if we set P to be U plus C NCI, then when we integrate the index J, Cj grab P times N is equal to negative J, right? because we can certainly choose find these functions u and vi, and then we are going to choose constants, and then we construct p in this way. Then this p, because the equation is linear, it certainly solves the equation. And then we are going to choose this constant ci so that this p satisfies this relation. So that's is going to be the condition that we are required. So let's see if we can choose this constant ci. So let's plug this function into the integral. Then what do we have? So we have that the integral on the boundary of hj, then u times n is sigma plus summation I1 to n ci times hj gradient vi, and we want this to be -2 times the area of hj. There's nothing I did. I just plugged this expression into the integral. And then let me move the first term to the right hand side. So we have the summation from I equals to 1 to n integral hj gradient vi times n the sigma times ci is going to be -2 hj minus hj w times n the sigma. I just moved the first term to the right hand side. So this is a linear system. We can write the last equation as a matrix dot product with a vector c equals to b, where the matrix is ji component is going to be this integral in the bracket. And its I component is ci, and b its I component, j's component is just whatever we have in here, 2hj minus So if we can show that the matrix A is invertible, then there is a unique C that satisfies this equality. That means for that C, this equality is true. That means the P constructed in this way satisfies this. So all we have to do is the matrix A is invertible. So we are going to use the Cauchy-Green circle theorem. So let's see like the components, if the diagonal components are dominating. So let's see the diagonal components, A of j, g is going to be, so we can just replace this I by j. So we integrate hj of gradient vj times n sigma. Then, well, what is vj? Vj have the domain V, and we have a hole, and we pick the jth hole here, and then Vj in this equation, it attains its maximum here, and Vj is harmonic function.
It's one.
It's one. Sorry. Yes, thank you. It's maximum here, and Vj is harmonic indeed. So when you look at the normal derivative in this direction, then this is always strictly positive, right? But here, as I mentioned, the n, the vector n is outer normal vector with respect to this domain. So n is always pointing outwards. In this case, the integrand is always strictly negative. So it's not, I mean, like we are assuming the boundary is smooth, so we can use the Hopf lemma. So it's strictly negative, not just less than or equal to negative. So we know that each diagonal element is always strictly negative. Second, if we sum, so matrix A, so we want to show that the diagonal element is dominating. So when you have these components, then we are going to sum all the elements in the jth column. So let's sum I from 1 to n a ij, and that is gonna be where is a I comma j a here. So we are going to wait. It's confusing. So the first index corresponds to the whole. Okay. So we sum according to the first index. So we have that the summation of I1 to n integral hi grad vj n is sigma, right? Any questions so far? So I comma j is going to be that summation. Summation is going to be. Well, let me flip the direction of n. So we are going to have negative of 1 to n hi grad vj times negative n is sigma. Right. So I put the negative. So I flipped the direction of n, and I put the negative sign, so nothing changes. And we are going to add something. No, subtract something. Subtract the boundary integral on the outermost boundary, which is denoted by d naught. And to keep the equality, you have to add the same thing, right? Then what is this? This whole thing is going to be, we integrate the normal components on the every boundary. right? This direction. So that is just the negative of the integral on the boundary of the patch. And then we have this side. And then you can use the green theorem or whatever. So this is just negative Laplacian of V. And this is 0, right? I agree. This is
The sign of the normal vector.
so like whenever we have normal vector on the boundary integral,
Okay.
so that is always orthonormal vector with respect to the domain. So here this n is the outer with respect to the whole.
And then it seems to be.
Yes. So this n is gonna be the this negative n is gonna be the outer with respect to the domain patch D, but inner with respect to the whole. And I shouldn't have erased, but Vj was harmonic in D, and Vj was 1 on the jth boundary, and it's 0 on other boundary. Right? So this is what I erased here. So because Vj is harmonic, so the first integral it vanishes, and then when you look at the second the term, then Vj is harmonic and it attains the minimum on the boundary. Yes.
Because there's no value.
Yes.
Right.
Right.
So I will be with that.
Yes. Someone has to take care of.
I will do it.
Oh, you already got it. Thank you.
I'm gonna do that. Okay. I'm now.
Okay. Thank you very much. I'm sorry. Okay. So where we are. So we have this integral. The Vj attains the minimum on the boundary, especially on the outermost boundary. So this is always strictly negative. So we get this guy is strictly negative. So we know that each diagonal element is negative, and then when you sum all the column elements, that is still strictly negative as well. So this equality matrix A is inverted. From 1 and 2. Follows figure showing circle here. Matrix A is okay. So this proves the first part of the lemma, right? Sorry? What is positive?
No, the elements that are positive are positive. And
The other elements, non-diagonal element? It could be positive. Yeah, total sum is.
Also, the matrix of all minus ones satisfies this condition with the group is clearly number. I think we need positivity on there.
but that's true by default.
Yes.
Minus two
Everything is not invertible of some spectrum. But since the elements that are not in there are positive, by the same argument as in one. Because it's the minimum instead of the maximum.
It's minimum instead of maximum. I'm sorry. Can you? I'm sorry. So what are you saying? Positive? So each element is positive or what?
Yeah, if you have one element matrix which is constant minus 1, minus 1, minus 1, minus 1.
Yes.
It will satisfy 1 and 2.
1 and 2. So like -1, -1, -1, -1.
need another condition.
All right.
And this is like Aij when I is different from J are positive.
Ah, right. Yeah, right. There's a missing part. Right. The other element, this guy, it should be positive, right? Yes. Right. Okay. So, but yeah, as you mentioned, same argument says that okay, missing parts. So Aij is positive. I is not equal to J. Okay. So the same argument holds by the maximum. Okay, so that's the missing part, right? Okay, thank you very much. So yes, so we proved the first part, and then let's move on to the second part. So we know that we can choose to Ci, so that's if the function P solves this equation, then it satisfies this relation as well. And then we have to show that such P satisfies this estimate. So let me first give you the motivation. Why do we need this extra condition? So why are we looking for such function P? So the motivation. So we are dealing with a non-simply connected set domain, and earlier, like when we did the symmetric, when we did the simply connected set, we perturb this patch using the continuity equation with divergence free vector field, right? So basically, this is going to be just a transport equation because the vector field V is divergence free. So it means that we perturb this patch so that it preserves the area of the patch, right? And then we use V to be x plus T, where T was defined in this way for the simple connected set. But for the non-simply connected set, for non-simply connected set, H1, H2, we are going to use the field V. It preserves the area of the patch, but also it preserves the area of the holes as well. That means that we choose V so that its divergence is free. And when you look at the flux on each boundary, that is 0. Right? So it means that if you run this continuity equation with such vector fields, then of course, like the shape of the domain changes, but the area of the patch doesn't change, and the area of the hole doesn't change either. Okay? And so as before, we are going to replace this vector field V to be x plus gradient of something. So then what condition do we require on P? So let's plug this into here. Then we get I x dot n plus hi z t and is sigma. But this guy is exactly 2 times the area of the hood. So when you move it to the right hand side, then the boundary integral is equal to negative 2 times the area of the hole is the the requirement on the function p. So that's the demonstration. And there's a remark. So as I mentioned, this can be thought of as a projection in the sense that for any vector field V such that divergence is 0 and the flux is 0, we have that omega minus x L2 on B is always greater than or equal to x minus x plus grad T L2. So if we add grad P, then we can certainly get a vector B that satisfies the divergence precondition, and there's no total flux. For in such class, this is the has the closest distance to the vector S. Any questions so far? Or like, so, if not, then let's do the second statement. So I'm going to define, so first, the CI boundary values, they are strictly positive. Why is this so? Because the function let's suppose one of the CI is negative. Let me more reverse. Suppose the contrary, that there is I such that CI is strictly negative or less than or equal to 0, then you can pick the smallest one, pick J. J is the smallest one, and certainly Cj has to be less than or equal to 0. Then when you look at this condition, on the J boundary, then this has to be negative 2 times the area of hole. So this has to be a negative number, but because the function P attains its minimum on the J boundary, so when you look at the normal velocity, the normal derivative in this direction, it has to be strictly negative. So when you look at the derivative in this direction, it has to be strictly positive. This guy has to be strictly positive, so we get contradiction. Right? So its CI has to be positive also. P is always greater than or equal to 0, still it's because of the maximum principle. We cannot obtain any like, negative numbers in the domain. So then we are going to define function g to be the measure of the superlevel set. P is greater than K. First, G not is going to be D. And then we are going to compute the G in two different ways. The first one is to use the core area here. GK can be written as the integral of using the core area here. Integral from K to infinity 1 over gradient of T the sigma ds. So this is just imagine that you have a patch E here and let's suppose this is a level set corresponds to P is equal to K, and we have a smaller level set corresponds to P equals to K plus CK. Then, so we want to find the area of this domain, but when you look at the infinitesimal here, then this length is corresponding to the surface measure, and this length is exactly 1 over gradient P. And then we sum every like infinitesimal boxes, then we get the area of the superlevel set. And so we just take the derivative in K. It's going to be a negative surface integral K. Because K is down here, so we get the negative sign. So now we're going to estimate the K in different ways by using the fact that P solves a certain elliptic equation. GK is as the integral of 1 on this level set. Nothing changed, just directly follows from the definition. Then we can replace 1 by negative 1/2 times Laplacian of P, because Laplacian of P is negative 2, so this is just 1. And then we can do the Stokes theorem. So this is the boundary of this superlevel sets. Negative 1/2 gradient P times n. This. So what are the boundaries of this set? So let me again draw a non-simply connected patch. Let's suppose we have some holes here, H1 and H2. And here's P is value set constant and C1 constant. And suppose K is between C1 and C2. So you can imagine that the level set is going to the super level set. The level set corresponding to K. It's around the larger value, this guy, right? Or maybe there's some level set that's around C1, but there is going to be another level set inside, so that in this area P is less than K, so the super level set is going to be only this like onion ring region, right? So when you look at the boundary, it doesn't contain the boundary of the super level set, doesn't contain the boundary of C1. But if P is always bigger than K on this area, then the boundary of the super level set must contain the boundary of H2. So this boundary integral can be split into the summation of the boundary of the holes, so that Ci is bigger than K. So we integrate the boundary of Hi -1/2 sigma plus we have the boundary that corresponds to the letter set. P equals to K. Right? So this boundary, it includes only the boundaries for which the P's value is greater than K. So in this case, it includes this guy, but it doesn't include this guy. And this sum over I, but the i's they satisfy Ci is greater than K. And now we use this condition that it satisfies this one. And so here I made a mistake. So we have to multiply by negative, right? Because because of the direction of the normal vector. So does it make sense? Because here this n, for example, it's pointing inwards, but like when I write in this way, then we promise that the n always pointing the out normal. So we have to like multiply just negative sign. So this is going to be positive, and this we keep the negative sign here. So then this guy is going to be negative 2 times the area of the hole. So 1/2 times negative 2 Hi. And we keep the same thing. This is just sum I Ci K H plus integral P equals to K. And let's look at this. On the level set, the normal vector is always parallel to the gradient of P, right? And when you look at this level set, for example, so this is the area where P is bigger than K. So the gradient is always pointing inwards. So the normal vector and the gradient, their direction is parallel, but they are pointing the opposite direction. So this guy is gonna be negative of gradient P, it's negative, right? So we have negative and another negative here. So 1/2 times P is sigma. We get this is GK. So then therefore GK minus I think I made a sign mistake somewhere. Let me check. I kind of think that I made a sign mistake. Okay, let's see. Let's just keep going. So we move this term to the left hand side. So we have the I CI of HI is equal to P K 1/2 P. I think this should be positive. Yes, logically. Sorry?
There should be a minus there.
There should be a minus here.
It comes from the previous. Okay, it's okay. These are 2 minus 2, so.
Right. Right, thank you very much. So there's a negative sign, so we must have negative. Right. This has to be positive, so thank you very much. Okay, so we get this.
You have to come to the numbers.
I'm sorry. And then we get this as well here. So let me multiply G prime on here. So G prime K times G K plus ICI to the K HI is going to be 1/2 times gradient P, the sigma divided by 2K 1/, gradient P is sigma, right? And negative, because there's a negative sign here. So let's look at this guy. So we have that so let's look at the surface integral on the level set. So that gives you the perimeter of the level set. And then we can split 1 into the P times root P times 1 over P. And using the Cauchy-Schwarz, this is sigma that times sigma. So we can square them, so that's, we get this. Therefore, this guy is always less than or equal to, no, bigger than or equal to the perimeter. I don't know how to. Yeah, let me just use the this absolute value symbol to denote the perimeter. Okay? But we have a negative 1/2. So we flip the direction of the inequality. We turn K minus K. Let me omit the indexes here. HI is always less than or equal to negative 1/2 to perimeter square. Then let's recall the isoperimetric inequality. That means that if you look at a closed curve, its perimeter is always greater than or equal to 4 pi times say let me use dk. K, where dk is determined by its boundary equal to the closed curve. So that means that this dk is the area here. It includes the hole, right? And in this case, it corresponds to this strip region, right? So what is dk then? So dk it consists of the level sets area. P is bigger than k, and it also includes the area of the holes. But the holes, it has to satisfy that its boundary value of P is bigger than K. So it is exactly the response to this guy. Union I, Ci is bigger than K, Hi. That means the area of the K is K plus summation H. So where are we? So we have this, and we have this. Therefore, K k plus r is always less than or equal to 2 pi times the area of D, where the area of D is exactly k plus summation of h. Right? So we can cancel them out.
It's also minus
Uh,
on the right side.
right. Right. There should be a negative, right? Right. The GK has to be decreasing function because we are looking at the super level set. Right. Right. Thank you very much. There's a negative sign. Okay. That's a negative. So let's recall the definition of GK. Let's recall GK was the area of the super level set. This is always like a non-negative number. So in this case, G, and also we have that the G0 was the area of the patch. And then GK is always less than or equal to D minus I. Okay. We take only the positive parts. That's because G is a decreasing function, but at 0, its value is the area of the whole domain, but it decreases, but the slope has to be steeper than 2 pi, right? So then you get the expression, because it cannot like go beyond to the half plane because the GK cannot be a negative number. We get this. But what are we looking for? What are we are looking for the area of the integral of t on d. Let me use the layer cake representation. So we can write this p as from 0 to px d, say t px, right? So here I replaced this p by the integral from 0 to px of 1. This is just px, and also please remember that p is always like non-negative number. Like, so we can just integrate from 0, and then we can replace this 1 by 2 infinity. T is less than 0 T yes dt x. Okay. So I just replaced, I extended the integral domain from this certain interval to the whole real numbers, but I replaced this one to be just a characteristic function that is defined on a certain interval. Okay. There's nothing technical thing here. And then we can do the Fubini theorem. We can interchange the integrals. So we integrate from 0 to infinity, and then we integrate on d. The px is bigger than or equal to. Let me just delete the equality. Let's put the strict inequality here. T, yes, t, and this guy is exactly g of t. Right, and we know that G of K is always bounded by this, so this is always less than or equal to its positive part, and then you get. Let me skip the interior part. Elementary. So we are kind of done. So we get the estimates here. So we need to show that the equality is attained when a disk or analysis. So where can we get the equality? So we have used a lot of inequalities, but there are two parts where the equality sign is actually important. So one is here, and the other one is here. Okay. So for this one, this two. If we have quality and from here the isometric inequality, the equality is achieved only if the disclosed curve is a circle and the domain is a disk. Then is a circle. But still, it doesn't give us a radial symmetry because imagine you have a disk as a domain, but what if its level set looks like this? So, I mean, every level set is a circle, but it doesn't have to be like radial symmetry. It can be like skewed a little bit. But to fix it, we can look at this. So to have the equality here, the Cauchy-Schwarz, the equality is achieved when like these two values are equal and constant. So this effect is coming from isometric quality and also we have that gradient T is constant. So in that case, we cannot have a skewed level set, something like this, because in this case, the gradient is much small here, but the gradient is large here. It cannot happen because the gradient has to be constant on the level set. So in this case, we get radial symmetry, radial function here. I think. Any questions? For animals, so what it says is that yes. So okay. So what it says is that the gradient P is constant on the level, on each level set, and each level set is a circle. So if you have a hole, then why do you think that the analysis is not? I mean, so analysis is not, excluded by this. Right. Okay, so let me argue it this way. Let's suppose your domain is not a disk nor an annulus. Then we cannot have the equality here. Right.
Yeah, I guess there is a bit more dedicated.
Actually, like in the paper, we proved more rigorous way, but in that case, like the notation becomes too messy. But like intuitively, this is the arguments. Or any other questions? And as I mentioned, we proved this the first statement and the second statement, and that implies the lemma that we were supposed to prove yesterday. So let's do the non-simple connected patch case. Is located the angular velocity 0. So as I promised, we have to prove this as well. This difference, and then it takes another like just a few more hours. So I decided not to because I want to do something else after this. So we only look at the negative, the non-positive angular velocity case. In this case, then is a disk. The proof is very simple. So let me recall that this quantity I so as I mentioned that if since the patch is rotating with the angular velocity omega, so the velocity function that is defined should be the convolution with the patch minus omega over 2x squared satisfies constants on the boundary of this. We can a patch D here and another hole. So psi is going to be some value A1 on the outermost boundary. Yes. And psi can be another constant on this boundary. And another constant A3 on this boundary. So A1, A2, A3, these are constant, but they are not necessarily the same. All we need is that the boundary is a level set of the psi here. So this is what we know. And then, so as before, we are going to compute the variation. But let me skip the part, but let's look at this quantity I, which is defined to be x plus level p times x on d. So this is the same quantity that we saw in the first variation of the functional that we defined last time. Here, of course, the p is a solution to this equation where the constants are picked so that the additional condition is satisfied. Yes. Sorry?
When you say analogous, you mean a concentric analogous, or it could be a disk minus a disk which is not centered at the origin?
No, actually, if omega equals to 0, then the path doesn't have to be a disk, doesn't have to be centered at the origin, because the station solution you can just move, translate it. But if omega is strictly less than 0, it has to be centered at the origin, because we are saying that the patch is rotating about the the origin. So is that your question, whether the disk has to be centered or not?
What do you mean by annulus?
Annulus, just annulus, like the patches.
The full disks are.
Yeah, they are concentric. Yes, right.
So can it be more than 2 disks? Like can it be unit 2 annulus?
Yes. Actually, in our paper, we prove much stronger results. So if we can you can even remove disconnectedness if you have disconnected, or in general, if your stationary or like rotating solution looks like this one, where you have a different vorticity, not just one. In that case, it has to be radially symmetric. So the only possible case is you have an annulus here, and another connected component has to be an annulus like this, and this annulus, they are concentric. So everything has to be concentric. Everything has to be this trivial. And possibly there's like one single disk. But let's just stick to the connected case for now. Okay, so on the one hand, we claim that I equals to 0. That's because we can just use the integration by parts. So I is going to be, let's move this gradient to the left hand side. That is going to be boundary I and x plus squared p, and normal vector phi x is sigma x minus b divergence of x plus p phi dx. Right? So this guy is 0 because x plus red p is divergence free. And for this guy, you can split into, so let's still denote the outermost boundary is partial of d naught, and then the inner boundaries are denoted by partial of hi. So we can split this into the integral on the outermost boundary plus the inner boundary integral like this, and wait, the normal vector, and we have to put the negative sign here, right? Because the direction of the normal vector changes. And here I forgot to mention, but we can without loss of generality, we can assume that psi, this constant, is 0 on the outermost boundary. Just simply we can replace psi to be psi minus a1. When you take the gradient, the a1 it vanishes. So let's suppose the outmost boundary value of psi is 0. That means this guy is 0, right? Because psi is 0 on the outermost boundary. And we know that the psi is some constant values on the boundary, the inner boundaries. So that is going to be constant ai. Then we have and sigma. When you look at this integral, the x times n is going to be divergence of x. We integrate this in the whole, right? The Stokes theorem that gives you 2 times hi. And we know that this p was chosen so that when you integrate the boundary integral is negative 2 times hi. So when you add them up, then this is 0. So we just proved the claim, so I has to be 0 for this. And of course, you're going to show that I can be 0 only if the patch is a disk or annular. So now we split. So let me erase this part here. And then let me split I into the following. So x times gradient of n minus omega over 2 x squared dx plus the p have negative. So when you if the gradient hits this guy, then we get the omega times x, right? So we can write it as the grad p times x dx. So I just did the distribution. So I distribute x to psi. So psi, this is exactly psi, right? And then when I distribute gradient p to psi, so like when gradient p hits this one, then that is here. And when the gradient p hits this one, that is just here. And then this is going to be, I'm going to split a little bit more, x times grad minus omega. So these two terms are coming from the first integral, and then we have the rest. The p plus x. So, as we did last time, this guy can be computed as exactly equal to d squared over 4 pi. So we flipped the variable x and y in the convolution, right? And then there's a like magical cancellation thanks to the structure of the differential potential. We get d squared over 4 pi here. Then we have omega x squared dx. And then we can do the integration by part for this guy. We get boundary E sigma minus P dx, right? Because when the gradient hits this one, we get the Laplacian of this one, which is the characteristic function defined on D. So this is just 1 in D, right? And we have negative omega. Okay. So let's look at this guy. So let me put this say larger. So large A can be split into the integral of the outermost boundary. Something this is not really important. Plus hi p times gradient d involved with n this sigma. I didn't write anything here because this is not important, because we know that the P is 0 on the outermost boundary, right? So this is 0. This P is 0. And okay, so here we have the negative because we flip the direction of the normal vector. So this guy is going to be, you know that P is constant on the boundary of the hole. So this is going to be negative Ci times Hi gradient Laplacian convolution times n. And again, the Stokes theorem says that this is negative Ci times summation I, summation over I, summation over I is going to be, we integrate on the whole of the Laplacian of the convolution, right? Just the integration of parts. And that is going to be negative Ci on the whole with this function dx. And this is 0, right? Because the whole is not included in the domain. In the whole, the characteristic function is 0. So we get just A is 0. Okay, then what do we have? So we get this vanishes. So we get the quantity I is, let me collect this guy together. Is squared over 4 pi minus yes and minus omega times, let me put this guy and this guy together. Plus x. I'm going to claim that gradient is P x dx it's negative is always less than or equal to x squared x. So if we have this, then we know that this guy is always like non-negative, and then we are assuming that the omega is a negative number. So this is non-positive, non-negative number. So this whole thing is like non-negative number, and then we know that this is non-negative, and it becomes 0 only when the patch is a disk or a manifold. Okay. So to show this one, so it applies to show that. We compute left-hand side. So I mean, this is quite obvious because we can replace. So as I mentioned, like adding grade P is a projection. So if you imagine like in finite dimensional, then maybe the space corresponds to the divergence free vector fields, and then this corresponds to the vector field such that divergence is -2. And whatever we have a vector here, then we can project this vector into a free space by adding gradient, right? So in this case, like this inner product must be smaller than this one. Okay, so let's see this reversal. So we can do the divergence. No, the integration by parts. That is going to be on the outer boundary, and we have the inner boundary. P, no, X, and the sigma. Right, I have the negative sign, right, because we changed the direction. And this goes to 0 because P is 0 on the outermost boundary, and that is going to be summation. Summation of Ci is a constant that corresponds to P on the boundary. And then as before, we get X dot N, but this one is just 2 times HR. We get Ci, 2 times HI. And what is 2 times HR? 2 times HI is the, I erased, but times the integral of the whole of grad P and the sigma and negative, right? So we pick the constant so that this integral is equal to negative of this one. And then of course we can add the P, grad P is sigma here, because P is just 0 on the outermost boundary. So I just added 0. And then the whole thing is just, it's just that, because Ci is just P on the boundary, we can just plug this into the integral, like this, times, and then we also flip the direction of normal, grad P, sigma, on the boundary. And that is the square dx. Then what does it mean? So we have the negative grad P times x is always equal to this guy. But we can do the pressure shorts. That is going to be 1/2 times P. It's L2 plus 1/2 x squared dx. So this guy is always bounded by this one, so we can just move this one to the left, and we get P. It's always less than x squared. But what is this? Is equal to this one. This one. So this one is always less than the integral of x squared. So we get this. So let me finish. This is always non-negative number, and this can be 0 only if the path is a disk or animals. And we already have that the I erased